Alright, so far we've covered ionic bonding and metallic bonding. Now we're going to add covalent bonding to your repertoire. The major difference between covalent bonding is that they share electrons versus transferring or like free movement of the electrons. Okay, so octet rule still applies to covalent compounds, all right? But what will happen is the atoms involved in it will share electrons to fill their octets. All right, so sometimes, like that pair, they'll always be shared in pairs, and that will fill the octet of whatever compound we're working with. This really only works with elements that are close to filling their valence electron shells. So you're going to see nonmetals doing this. You know, things in group 4, 5, 6, 7A involved in covalent bonding. Another thing that is often not held true, because a lot of times you'll even hear scientists and things like that refer to ionic compounds as molecules. Technically speaking, this term molecule is only supposed to be used with covalent compounds. So ionic compounds are salts, covalent compounds are molecules. So here is what this whole sharing thing looks like. And we'll actually go over this whole Lewis structure thing that kind of helps sink some of this stuff in. But if you think about it, you've got your carbon. All right, it's got 4 valence electrons. All right, and then you've got hydrogen, which has 1 valence electron. So these guys can come together and share their electrons, like, well, that's covering up the other one, all right? But they can share, so like here's the, say this is the hydrogen electrons, and here are the 4 carbon ones, all right? So that's what the whole sharing looks like. They will always be shared in pairs. Now, you can form multiple bonds, all right? So another kind of shorthand way of drawing CH4 is a lot of times people will draw a line to represent a bond. So you might see the diagram look like this, all right? And that line represents those 2 shared electrons. You also have the option of creating 2 bonds, or sharing 4 electrons, all right? So oxygen looks like this, all right? And then another thing that might happen is you form triple bonds, all right? So between these 2 carbons, you can see that there are 6 shared electrons, all right? And then on the other side, there's a single bond to hydrogen. All right, so that's how you can represent single, double, and triple bonds, either by drawing out the electrons, like the pictures on the screen, or the shorthand way of just every line, every dash represents a pair of electrons. So here are some good things to make note of as far as comparing properties of your ionic and your covalent bonds. All right, so if you remember, ionic compounds had those really formally structured crystalline shapes, high melting and boiling points. They could conduct electricity when they were melted or aqueous. Most were soluble in water, and they are always made of a metal and a nonmetal. Covalent compounds, on the other hand, they can be gases, liquids, or solids. All right, so they're made of molecules. Especially since some of them can be a gas at room temperature, they have considerably lower melting and boiling points than our ionic compounds. They are poor conductors, Sorry, my cats are getting fed right now. So another term you can use is that covalent compounds tend to be insulators. All right, many are soluble in nonpolar liquids like fats and oils, and they are not soluble in water, and they'll be made of two nonmetals. So when it comes to naming covalent compounds, all right, you guys are familiar with the reasoning why we use these prefixes, because I bet you could tell me, or once I tell you, you'll definitely recognize, oh yeah, I've heard of those before. These are two molecules made from carbon and oxygen. All right, carbon and one oxygen is the gas carbon monoxide, which is incredibly poisonous. The other one, carbon dioxide, is the gas that we breathe out. All right, so when it comes to naming and formula writing in covalent compounds, the formula has to tell you how many of each atom exists in the compound. All right, because otherwise, if I just said carbon oxide, I wouldn't know which one of these I was dealing with. So that's why we use these prefixes. All right, so these are probably prefixes you're familiar with, because it's the same prefixes you pretty much use for shapes and geometry. One that I know people tend to mix up is this one, because we're used to like quadrilateral, but in chemistry we use the prefix tetra, like Tetris, for 4. So I would definitely write these down. And then, honestly, you pretty much use these all the time to tell the number. The only exception, the only time you leave off a prefix is if the first element is singular. So both of these are carbon without a prefix, monoxide, which means one oxygen, and carbon dioxide. All right. So if we needed to name something like there's a compound that has this formula. All right, this would be diphosphorus pentaoxide. All right, so if you only get to skip mono if it's for the first element in the formula. All right, otherwise you should always be using those prefixes, second element, first element, always. So let's do a little practice. All right, so like I actually just did this one, pentadiphosphorus. First element keeps its name like it's from the periodic table. And then the second element, just like with ionic compounds, gets that "-ide" ending. All right. The first one on the other side, we've got boron. There's no prefix, so that means there's just one boron. And then trifluoride. That's going to have 3 fluorines. All right. You try 6. See if you can get those. So number 6, this is going to be dinitrogen tetraoxide. All right, and then bromine trifluoride, really similar to our other one, BRF3. Right. I'd say go ahead and try this one too, that way you can see what it's like when you don't have just one in the first element. All right, so this is going to be P4O6. So if you need some more practice, you can always, if you aren't sure, you can always look these things up online after you've tried making it, or talk to me. We can work these out together in a help session or something. So another thing you want to be able to do is identify based on either the name or the formula if something is ionic or covalent. So the trick to this is what kind of elements go into it. Ionic is going to have a metal and a nonmetal. Covalent is going to be all nonmetals. All right, so pretty much if you see a metal in there, then you know you're dealing with ionic. And I still haven't fixed this. That's not a real compound. Sorry. All right, so Al2O3, that's aluminum and oxygen. That has a metal and a nonmetal. So that's ionic. CH4, also known as methane. Carbon and hydrogen, both nonmetals. These are things that you can look up on your periodic table. So that's covalent. Another good way to use things is that if you see prefixes, that's another sign that you are dealing with a covalent compound, because we don't need prefixes in our ionic compounds. So magnesium oxide, no prefixes, and you can double check it, magnesium's a metal. All right, you try the next two, see if you can get that correct. All nonmetals, iron is a metal. All right, water, liquid at room temperature, so low boiling point. And then this last one is you've got your metal potassium, and then it happens to be attached to a polyatomic ion. But again, it's ions, so we know that's ionic. So the sort of question you can run into using this is, which of the following have the lowest boiling point? So here, you've got to ask yourself, okay, what type of compound tends to have low boiling points? Is that ionic or is that covalent? Hopefully you said covalent, so I'm looking for a covalent compound in our list. All right, so that's probably pretty obvious because we've talked about this example, but what you want to do is find something that's all nonmetals and make sure the rest of your choices have metals. All right, so sodium, magnesium, and calcium are all metals. Carbon dioxide is your answer here.